So the third and the fourth learning outcome is I want to understand what is science and what is the process of the scientific inquiry, and how do we use scientific methods to answer questions. So science is our way of asking and answering questions and testing ideas, okay, through evidence gathering. So science usually starts with a problem. Unfortunately, most of the time it starts with a problem. And scientific method is a method of inquiry summarized as ongoing process. So this is a typical process of a scientific inquiry. First, we see this problem and we make our guesses. For example, we see fish dying in the river. Our hypothesis would be they died because of the pollution, or they died because of the acid rain. They died because of the algae blooming. So there's different guesses. How do we know our guesses are true? We have to do experiment and gather data, and later on we analyze the data and to see if our hypothesis is true. If not, let's say it doesn't support the hypothesis, the fish are dead not because of the pollution. Then we go to another guess, another hypothesis, that is because of the algae blooming. So it's going on and on in this circle like this. And talking about science, not the daily life, okay? Observation is using senses or extension of senses to record an event. Example would be, I feel hot. And extension of the senses would be thermometer, right? Where we measure the temperature and know how hot it is. And hypothesis is a proposed answer. It's a guess to a scientific question, which can be repetitively tested. If we test it, it's not true, we abandon that hypothesis. If the hypothesis is true, it could be tested over and over again. And we know the thermodynamics, the first law, second law, that exists for hundreds of years. We test it over and over again. It's always true. Observation of the problem often occurs accidentally. I want you to read this story in the textbook to see how this geochemist, Mr. Cal Patterson, discovered how evil the lead in the gasoline is. He didn't mean to investigate the effects of lead. He just accidentally discovered it's really bad. It's coming from the gasoline. It's contaminating his samples. He tried to do these nice experiments to establish the age of the Earth, but he discovered the contamination of lead. The true data is a must for science. There's no wrong or right, bad or good data. Real data is equally important. Maybe your experiments are not working out, okay, because those data do not support your hypothesis. And don't feel frustrated. That's one way of exploring that at least tell you that way is not working and you can try a new way. It's not that if the data is supporting and you got excited, but the data supporting another story that is equally important. And one way to set up observation to test the alternative explanation is the use of a controlled experiment. So what is a controlled experiment? I'm going to use one example here. It is also in our textbook. Please read it. Observation. What is the problem here, guys? After you read the textbook, you will know the coral reefs are dying. So your guesses will be contamination of the ocean, increase of the temperature of ocean, or the ocean become more acidic. That's your hypothesis. Your hypothesis sounds something like this. The coral reefs is dying because the temperature of the ocean is increasing. And then you do your experiment. And don't forget the controlled experiment. The control, you have one nice group of coral reefs, right? In the ocean water, the temperature is constant all the way, and you have another group with ocean water, the temperature keep gradually increasing, and you observe in your control group, your coral reefs should not be dying. Okay, if they are dying, then your experiments are wrong. So in the test group, okay, with the increase of the temperature, and you will observe if the coral reefs are dying or not. So that's one example. Another example, let's say you see the cattle have tumors. Okay, all your cattle start developing tumors. So your hypothesis is it's because the river close to them is contaminated. So your control group should be a healthy group of cattle drinking the water that is not contaminated, and your test group should be the cattle drinking the water from the contaminated river. And then you compare the two groups and to see the occurrence of the tumors. Okay, so at last the results should be either supporting or rejecting your hypothesis. The last thing I want to talk about is a model. Okay, model is a simulation, calculation. Models assemble data, attempt to assimilate what actually happens. So on the left side of the slide, if we try to understand the current weather patterns or global climate change, we dissect the whole atmosphere into small units, like those little square cubic. And then we calculate the parameters and characteristics in each small unit and put them all together so we have an understanding what's the trend of the global weather. And the weather models, the global weather models are constantly revised. For example, we are tracking Marco and Laura, right? And they are tropical storms, and then they increase to Hurricane 2, and then they decrease to Hurricane 1. We have to constantly tracking the change in the atmosphere, and we have to be constantly calculating so we know where they make their landfalls, when they're making their landfalls, and as we watch TV, right, and we see those weather forecasts, they keep changing their story, and they keep updating us, right? So what are challenges to good science? Fraud, pseudoscience, bias. Bias is unreasonable thinking. That means you're thinking one way and neglecting the whole picture. And we receive a lot of misinformation from the social media, from the news, from our government, from the leadership. And it is you, a scientist's obligation to examine if those information are true or not. Let me go back to this slide. So fraud just means to deceive people. They are just false. And pseudoscience, it doesn't mean necessary to deceive anybody, but it's either part of the information or it's the wrong information. That's a pseudoscience. And bias, as I said, you're inclined to pay attention to one way and neglecting the whole picture. So the last thing I want to mention is a peer review. For example, I'm a structural biologist. If I want to publish a paper, I'm going to let my expert colleagues, okay, for example, I work for Baylor College of Medicine, I will ask my peer in Stanford University, in Harvard University, to look at my paper to see if it's making sense and to see if it can pass to be published, pass the examination, the reviews. So that concludes the third and the fourth part.